So here we're getting into our first math and calculations of this unit. The gas laws hopefully are very familiar from first year chemistry. But we need to remember that the only equation you're given on the equation sheet is the ideal gas law. So we do have Boyle's law, the relationship of pressure and volume, Charles, which is volume and temperature, Gay-Lussac's, pressure and temperature. But as you do those, sometimes people tend to kind of mess up what is times what or on top or bottom of those. So you either need to really take the time to commit those to memory, to practice them, to remember those, to make sure that you don't make any mistakes with those, or recognize that the ideal gas law really can be rearranged or substituted in to come up with this equation. So I'm kind of starting over here. We've got PV equals nRT. Well, if I am looking at this situation, it's the same gas and it's also at the same pressure throughout. If it doesn't tell me the amount or the pressure is changing, I can know that those are constant. So what I would want to do is kind of set equal or set everything equal to the amount. So when I rearrange this and have PV over RT equals N, that's saying that the moles that I start with is equal to the moles that I end with. The other things that cancel out on this is the R is the same, obviously, the whole time before and after. If I had a pressure that was changing, then I would keep that. But since the pressure also doesn't change, that cancels. So the Charles, Boyle's, and Gay-Lussac's law really are just variations on the ideal gas law, knowing that our moles and maybe something else is constant. So what this ended up as V over T at the beginning is equal to V over T at the end. So it's definitely worth the time to take that moment just to make sure. If we're looking at pressure and volume relationships, PV equals nRT, well, then the R and the T would cancel and be P times V equals P times V. So they are different. It's not just always a top and bottom ratio for pressure and volume because it's inverse. They're next to each other in the equation. But then over here, I've got the equation with the numbers plugged in. Note that Celsius has to go to Kelvin, Celsius has to go to Kelvin, and then we just solve for our unknown. So it does show you on the equation sheet how to get from Celsius to Kelvin. We're adding 273, but just make sure that you kind of slow down and look at that. Every now and then they'll give you Celsius temperatures in the 2 to 300s, and people kind of default to think, oh, those are already big enough, I don't need to convert them. But it always has to be in Kelvin. Or sometimes it'll give you a Kelvin that's really, really small that people recognize or look at and think of as a Celsius. So just pay attention to the units, especially on temperature. In our next scenario, we are changing from one gas to another. So we could write this as a chemical equation or just kind of look at the subscripts to think about our mole ratio. So we've got a volume, we've got moles of one gas, any certain pressure and temperature. Now we're looking same temperature and pressure, so that's not changing, but we're looking at a different thing. The subscripts of 2 and 3 tell us that it's not a 1-to-1 mole ratio. It's a 2 to 3 or 3 to 2 mole ratio. So for that, you could convert from moles of the one to moles of the other, substitute that into the PV equals nRT equation and solve for your volume. Note that here it's 25 Celsius. That's standard thermodynamic temperature, but obviously that's different than STP for gases. So just paying attention, plugging it in. If it doesn't specifically say STP, we don't want to use that 22.4. But another important thing is based upon the idea of Avogadro's law is that amount is directly proportional to volume. So that 2 to 3 mole ratio is also a 2 to 3 liter ratio, as long as we're not changing our pressure or temperature. So I take my volume, multiply it by there's 2 liters of this for every 3 liters of that, and obviously get the same answer with unit. So both of these would be totally acceptable work. If you wanted or needed to write out the equation to get the mole ratio, it's important. But anytime you're talking about one gas to another, that's where our N is changing. So that's something to pay attention to. Here on the third example, we've got hydrogen gas, volume, temperature, and pressure. Calculate the moles. PV equals nRT, really straightforward. Paying attention to our units. So we've got our temperature, changing it to Kelvin. When the pressure is given in atmospheres, we make sure that we match up the R for atmospheres. From there, it's pretty simple math. This is hard to get good estimates in your head, but do remember at STP that 1 mole occupies 22.4 liters. So when we change our pressure or change our volume, we should be able to kind of ballpark what our moles or liters be smaller than that. So we have higher pressure. Okay, we're squeezing it together a little bit more, but not quite twice as much. So what would that do to the moles? In terms of multiple choice, many times in multiple choice, we're going to be at STP, kind of like the problem down here, where you just have to kind of get close enough or round off. But you can still use the ideal. And really what you're doing more than trying to round exact numbers, because R is always hard to deal with, is thinking about, am I higher or lower than STP in terms of temperature and in terms of pressure? And what would that do to my moles or to my liters? The other thing is that if you need to be slightly more precise than that, rounding off R to like 0.1 or to 60, depending which value you're using, or the 8.314, rounding that to 10, just doing the quickest math that you can is normally going to eliminate some of your options in a multiple choice. B is actually a good example of what could show up in multiple choice here, because the molar masses, the mole ratios, and molar volume all kind of line up for math that we could estimate in our head. So calcium carbonate makes calcium oxide and CO2. We're at STP, we've got grams. They like to use calcium carbonate a lot because it's got a molar mass right around 100. So 150 over 100, that's about 15. Nope, that's about 1.5, a 1-to-1 mole ratio. 1.5 times 22, that comes out to around 33. Or here, since we're slightly above 150, 152, that's where the 34 comes from. Obviously, in free response, we would use our calculator. If it were free response, we would make sure we're paying attention to that mole ratio. And then also, whether it says STP or it gives us 0 Celsius and 1 atmosphere, we can use PV equals nRT, whether we're at STP or not. So some people are most comfortable using that all the time instead of worrying about the 22.4.